Hello everyone and welcome back. In this video, we are going to be taking a moment to talk about something important in this class called summation notation. Summation notation is just symbolic shorthand for a sum, hence the name summation notation. And as we've seen in the past couple of episodes, sums are very, very important to this class because this class is all about integrals, and integrals are just sums that have become very, very accurate as a result of having a lot of information and a lot of data to go into that sum. Summation notation gives us a nice convenient way to express big sums in small areas. To give you an example of what summation notation looks like, you're going to see something that looks a lot like this. So let's break down the anatomy of this summation notation and talk about what each of these little pieces, each of these little portions of this notation is doing. So the first bit of anatomy that I would like to draw your attention to in this expression is this Greek letter on the far left side that looks like a messed up E. This Greek letter is the capital Greek letter sigma. Sigma is the Greek letter S. S stands for sum, and so when you see this Greek letter sigma, you know that what is coming is a sum. That what is coming is instructions to calculate a sum. Now, the next bit of anatomy that I would like to draw your attention to is this quantity here, sort of at the bottom of the sigma, this expression I equals 2. And this one here is also going to be significant, this value at the top of 8. We're going to talk in a little bit about what this 2 and what this 8 are telling us to do. And then the next major piece of anatomy for this summation notation is this quantity right here, 2i squared. I'm going to demonstrate how I would interpret this summation notation and the sum that I would calculate based on what is presented to me here. So the first thing that I would do if I wanted to express or calculate the sum associated with this sigma notation, step number one of calculating this sum is to plug in all of the whole number values of I between, in this case, the lowest value here of 2 and the highest value in this case being 8. Where do I plug these values in? I plug these values into this expression here next to the sigma. I plug them into this expression here, 2i squared. So let me show you in more detail what I mean. I would start with the first value of I, the one given to me here at the bottom of the sigma, I equals 2. And I would plug that I value into my formula, and I would get 2 times the first I value, I equals 2 quantity squared. Then I would go up to the next whole value of I. So from 2, the next whole value of I would be 3. And I would plug that value of I equals 3 into this formula 2i squared. So now it's 2, 3 squared. I would continue. Next value of I would be 4. So I would plug in 2, 4 squared. Next value would be 5. I would plug in 2, 5 squared. And I would carry on to 6 squared. I equals 6. To 7 squared. I equals 7. And finally here, 2, 8 squared, corresponding to I equals 8. And that is where I would stop. I would plug in all the whole values of I between I equals 2 all the way up to I equals 8. because 2 is the value of I given to me on the bottom of the sigma, and 8 is the value of I given to me on the top of the sigma, and I would be plugging those values of I into this expression right here, 2I squared. So that's step number 1 of calculating a sum associated with given summation notation like this. Step number 2 is to take all those values and add them together. So here's the sum in the summation notation. All I would have to do is take these values that I calculated from I equals 2, I equals 3, I equals 4, 5, 6, 7, and 8, and just add those results together, and the result of that sum would be the value indicated by this summation notation. And you could do that using a calculator, for example. Now, just as a heads up, there is a name for this variable called I that we're using to sort of count out the various values in the sum. This value here denoted by I is called the index in your summation notation, the index. And so if you've ever done programming, if you've ever done loops, for example, for loops or while loops in programming, you may be familiar with this concept of an index that's being used to sort of keep track of where you are at in your process, to sort of count out steps in your process. Here we call it an index as well. Let's get a little bit more practice calculating sums that are described to us in summation notation. So here we have an index, which is being denoted by the variable k. It's traditional to use I, j, or k for indexes, as it is traditional to use x and y for other kinds of variables. So here let's experiment with a new kind of index called k. Summation notation, here is our sigma, signaling to us we're about to calculate a sum. Here at the bottom of the sigma, we're given our initial k value, k equals 0. Here at the top of the sigma, we're given our final k value of k equals 5. And here to the right of the sigma, we're given the formula that we need to plug these k's into, which is k squared all over k plus 3. If I wanted to calculate this sum, what value would I plug into this expression first? First, I would plug in this initial k value given to me at the bottom of the sigma, k equals 0. So in goes 0 squared all over 0 plus 3. Then I would increment that k value up by 1 unit. So now it's no longer 0, but it's gone up to 1. And I plug in k equals 1, 1 squared over 1 plus 3. Then I increment k one more time. It goes from 1 up to 2, the next whole value. And I plug in k equals 2, 2 squared over 2 plus 3. Then k becomes 3, and I get 3 squared over 3 plus 3. Then k becomes 4. Then k becomes 5. And once I hit 5, I stop. Why? Because 5 is the uppermost k value. 5 is the upper sort of limit on the k's given to me at the top of the sigma. Now once I've plugged in all of these values to this expression, then to complete the sum, I would just have to add these numbers together. And the result of that sum would be the value indicated in shorthand by this summation notation. So summation notation is really just a compact way, a nice compact way to communicate a sum. You could write all of this nonsense, or you could write this for short, and this is a lot less typing, a lot less writing, and takes up a lot less space. So summation notation is just a shorthand, a compactified way to communicate a sum like this one. Now let's get more practice with summation notation in a context that looks a little bit more like what we will encounter in this class. So in the previous several days of lecture, we have done sums using tables, tables of data. So let's practice using summation notation as it relates to tables of data. In this exercise, we've got a function described using the table below. The top row of the table contains information about our index. That's basically just being used to keep our place and keep our count. Here's the first value, the second value, the third value, the fourth value, the fifth value. Below that are x's, and the sort of position of the x in the table is being tracked by a subscript. So x sub 1, the first x in the table, the x associated with an index of 1, the table says to me your first x is 3. When the index changes to 2, when the subscript changes to 2, when the position in the table changes to your second position, this table is telling me that the second x value is 3.1. The third x value is 3.2. The fourth x value is 3.3, and the fifth x value is 3.4. So we have the index tracking position showing up as a subscript on the x's, and the x's corresponding to different indices is given by 3, 3.1, and so on. In the final row of the table, we have the corresponding outputs associated with each of those x's. So when the index is 1 and we're dealing with our first x value, the corresponding first y value is told to me to be -2 by the table. The second x value is associated with a second y value of -4. The third y value is 0. The fourth y value is 4. And the fifth y value is 2, being tracked by these indices here. Now with this table, let's go ahead and evaluate this sum given to us in summation notation, sigma, and then the lowest I value is 1, the highest I value is 5, and the thing that we are plugging those i's into is given to me here in function notation, f of x with a subscript of I. So we've seen that when we're using summation notation, the first thing that we do is plug in the lowest I value to the expression given to me here on the right. Now, in the expression given to me here on the right, the I value is a subscript. So the first thing I would do is I would plug I equals 1 into this subscript position and use that to replace the I there. Then the next thing I would do is replace I with its next value, 2, and I'm replacing it in the subscript because that's where I appears in this exercise. Then I am replacing I with 3 down in that subscript. Then I am replacing I with 4 down in that subscript. Then I am replacing I with 5 down in that subscript. And so adding these values together from 1 to 5, this sum would be what I'm asked to calculate by way of this summation notation. Now, f of x sub 1, according to my table, the first x value is given to me as 3. F of x sub 2, if I plug in the second x in the table, the second x in the table is given to me as 3.1. So let me use that information here. If I want to find f of x subscript 2, then I'm looking for f evaluated at an input of 3.1, because 3.1 is the second input. The third input, according to my table, is 3.2. The fourth input, according to my table, is 3.3. The fifth input, according to my table, is 3.4. So what I'm being asked to calculate, now I know, is equivalent to this sum. My function evaluated at these 5 input values. And then finally, from the table, I can figure out what outputs correspond to these 5 inputs. For example, according to the table, the output associated with x equals 3, the output is -2. My table tells me the second output is -4. My table tells me that the third output is y equals 0. Then finally, the fourth output is 1. Then finally, the fifth output is 2. So what I'm being asked to do is add these output values together. And so what do I have here? This is -6, that's +3. In total, the result of this sum is -3 units. So this is an example of using summation notation as it relates to a table representation of a function. But if you saw the review bite video, you know that there are two other ways to represent a function. For example, it's also possible to represent a function using a formula. For example, here we have our same set of inputs, index running from 1 to 5, inputs running from 3 to 3.4, but this time our function is described to us using a formula. So in this setting, let's also practice using summation notation and evaluating the sum described to me here. Now in this example, just like in the previous example, we are summing as I goes from 1 to 5. So I can sort of copy paste what I have in the previous problem because that is the same so far. We are summing as I goes from 1 to 5, f evaluated at all these different x values. Additionally, what has not changed from the previous example are the x values themselves. The first x is still 3, the second x is still 3.1, and so on. What has now changed is the information that we are provided to find the outputs associated with each of these x values. In this situation, we would have to use this formula to calculate each of these values of f of 3, f of 3.1, f of 3.2, and so on. Now f of 3 is easy enough for me to calculate by hand. If I plug x equals 3 into this function, then I get 3 times 4, that's 12. 12 minus 1, that's 11. But these other values, because they involve decimals, are a little bit too difficult for me to do manually, I think. So I'm going to go ahead and calculate those values off screen, and I'll be back in just a minute. So I did those calculations off screen, and those associated outputs are given by these values here, first 11, then 11.4, then 11.8, and so on. And then by adding all of those values together, the result of that sum would be what is being called upon in shorthand by this summation notation. Now, we also saw in the review, right, that there is a third way to represent a function, and the third way to represent a function is using a graph. So finally, let's get some exercise applying summation notation in the case that your function is represented graphically. So once again, here we have a set of inputs being described by a table. And here our index is running from 1, 2, 3, 4 to 5. And our x values have changed a little bit. Now the first x is 1, the second x is 1.1, the third x is 1.2, and so on. Additionally, our function x in this problem is being described using this graph, which is too large to fit on this screen. Hold on just a second. Using this graph. So let's go ahead and use this table and use this graph to evaluate the sum described to me in this summation notation. Sigma at the bottom I equals 1, at the top I equals 5, and then we're trying to evaluate f of x sub I. Now, once again, this summation notation is telling me to evaluate the function f at these 5 x values. And in this particular problem, those 5 x values have changed. Now, the first x value is 1, the second x value is 1.1, the third x value is 1.2, the fourth is 1.3, and the fifth is 1.4. Now to calculate each of these 5 output values, we are forced to use the graph to do that calculation. So let's go ahead and use the graph to get at least reasonable estimates of the outputs associated with these 5 inputs. Now, if I want to find the value of f of 1, graphically speaking, then I'm going to have to go to the graph of the function and find the location on the graph corresponding to a horizontal position of 1 unit. And that will be located on the graph right here, where x is equal to 1. Now if I want to find the corresponding output, all I have to do is look at the height of this point on the graph, and looking over to the y-axis, the height of this particular point is given by 0. What this is communicating is that if I plug 1 into this function, the corresponding output is 0. Remember from the review bite that the outputs of your function are the same as the heights of the point on your graph. So I plug in 1, I get 0, and that's what this point on the graph is telling me. Let's do the same thing for x equals 1.1, which horizontally is located right around here. If I navigate to the point on the graph that lives in this horizontal location, that would be right around here or so, and that point on the graph has a height of, let's see, this would be negative zero point 0.1, this would be negative zero point 0.2, down here is negative zero point 0.3. So I'm going to give a pretty rough estimate that this might be like negative 0.27 or some such, right here located between negative zero point 0.2 and negative zero point 0.3 in terms of the height. So I'm going to estimate a height of around negative 0.27, and that height of that point is going to correspond to the output of this function at an input of 1.1. Same thing we'll do with 1.2. Step number 1 is to locate the point on the graph that has 1.2 as its horizontal position, and the corresponding height of that point seems to be somewhere in the ballpark of maybe 0.48, just a little shy of negative 0.5. So that would be the output corresponding to this input. And repeat again with 1.3. That's a little bit below negative 1.6. So I might estimate maybe 0.62 negative for that height. And while I'm here, I'll go ahead and estimate the height of this point. Again, looks like just a little bit below negative 0.7. So I would estimate the height of this point probably to be around negative 0.72 or something. So putting those y values into their respective positions, this height of negative 0.62, this height of negative 0.72, the sum of these y values would be the value that is being asked for by this summation notation. So that concludes today's video. In summary, summation notation provides us with a compact way to represent sums. Very applicable to this class because this class is all about integrals, and integrals are just very intense sums. And the sums that are in summation notation are just like the sums that are involved with integrals. Those sums can involve functions, and those functions can be represented using tables, using data, but they can also be represented using formulas. That's what we've seen that before as well. And they can also be represented using graphs. And this graphical connection to summation is something that's going to be really important for us as we go forward into the next couple of lectures concerning a special kind of sum called a Riemann sum.